So this is part 3 of lesson 2.3. So if you take a look at this picture, all I want you to notice, or all I want you to do right now is notice about what you see. Okay, so we do have this box M sitting on a table. We do have, and I'll highlight it, we do have a force, right? This diagonal. And then we have these dotted lines, which are labeled Fx, and another one, which is labeled Fy. And we have this thing in the middle. If you recall that, that this guy right here, this symbol, is theta, right? That's how we pronounce it. It just means the angle. And we've seen depictions like this where we have something labeled with a subscript x and a subscript y. So these are just my components, all right? So now let's think about whether or not we can use the Pythagorean theorem only to solve for the components bx and by. All right, so given this diagram to the right, you have a resultant of 9.2 newtons, and then you're given an angle. I want to know if you can find this component bx, and this other component by, given that information. So remember, Pythagorean theorem is a squared plus b squared equals c squared. And I'll fix this little square right here. So if you're given that information from the diagram and you know Pythagorean theorem is a squared plus b squared equals c squared, do you think that you can solve for bx and by? So the answer is no. Okay? You do not have enough information to use Pythagorean theorem. However, you can do something else. So if you recall on our reference table, we have these special formulas that have theta on them, and they're in the back on page 6. So if you used ax equals a cosine theta, or ay equals a sine theta, then it wouldn't be a big deal. If you used either one of them, to find either bx or by, then you can plug it into Pythagorean theorem and you'll solve for the missing piece. So in order to use Pythagorean theorem, you need to have 2 out of 3 pieces, okay, in order to solve. So why we can't do this? Because you only have one piece, which is which is what we call the hypotenuse in math, but for us we call it the resultant. Okay, so when you draw a regular triangle, you have this right angle, this is a leg, and then this is your hypotenuse. If you only have either this guy and this guy, then you can look for this leg. However, in the following example, you only have the hypotenuse, and then you have 2 missing legs, so that's not going to work. All right, so that's why we'd have to use these 2 formulas right here. And to be honest, most often we should be getting used to using these component formulas because we did use them in the last unit, and we will continue to use them. So, just get in the habit of practicing. So now, how do we solve for the net force and acceleration when problems involve forces at an angle, right? So now this is a little different. So step 1, we're going to draw a free body diagram, always and always and always, okay? We draw free body diagrams to help us visualize what's going on, and it shows us all the forces that are acting on an object, so it tells us you're not going to forget anything, and it's going to help us do the math. All right, so it might be hard when you see words, but if you can put it into a picture form, sometimes that helps us more than the words do. So step 2, you're going to use the appropriate formulas to solve for the horizontal and vertical components, and these formulas can be found on page 6. The following formulas are right here. Ax equals a cosine theta and ay equals a sine theta. Remember, theta needs to be in degrees, not radians. So when you're using a calculator, make sure that theta is always set to degree, or angle is set to degrees, not radians, okay? Because radians will give you the wrong answer. Because we're talking about forces here, it's okay if you leave the formulas as ax equals a cosine theta and ay equals a sine theta, but when you do the math, Because we're talking about forces, it would make sense that we would label it as Fx equals F cosine theta and Fy equals F sine theta. Like I said, it's okay if you leave it set as capital A, but what I will say is that you can't be put in AX equals F cosine theta. You have to stay consistent. So with whatever letter you're saying this is, keep it that way throughout the whole formula, okay? Step number 3 is going to be to add in the horizontal force and the vertical force that you just found using those formulas into your free body diagram, and make sure that the vertical forces cancel out so that they equal 0. Our vertical forces on a regular free body diagram are the force of gravity, which points downwards, and the force, the normal force that points up. Okay, so we want to make sure that those guys do cancel out. The fourth step is making sure that you understand the horizontal force, Fx, is equal to the net force, okay? And I'm going to write here that this only happens when, when there is no friction, okay? If there is friction and we have to take it into account, then this idea is no longer true. But because we are not talking about friction yet, everything is going to be without friction. That means that my horizontal force, Fx, can equal the net force, and we have no problems, okay? We don't have to do any additional work. Finally, we're going to use an appropriate formula to solve for the acceleration that contains F net and the mass, and we know this to be A equals F net over m. Again, can be found on page 6 of our reference table, okay? So now we'll do an example. So the first one, a 10 kilogram wagon is pulled with a force of 6 newtons at an angle of 41 degrees. Solve for the acceleration of the wagon. So first, let's start marking up our text. So 10 kilogram wagon, and my force is 6 newtons. The angle is 41 degrees. So we want to solve for the acceleration, okay? Just like you would in math, we're going to underline the question. We're solving for the acceleration. So step number 1 was to draw a free body diagram. Before we even draw the free body diagram, I would just like to point out, let's write frictionless surface here. So the word frictionless means that there is no friction. All right, so that's why I'm saying in step 4 from the previous slide, the horizontal force Fx will be equaling the net force because there is no friction that we have to take into consideration. So I'm always going to draw my surface as this, just to indicate that that's a surface, it's frictionless. Okay, we draw on this dot. That's where all our forces are going to emerge from. So now let's draw in our normal force. So we have Fn and we have Fg. So in order for us to represent this force of 6 newtons, we don't actually draw it from the center, we draw it right from the side. So essentially, when you see a force like this, that just means that the object is being dragged or pulled at a certain angle, and we also have to add in our angle theta. So theta equals 41 degrees, okay? So we just did step 1. Now let's do step 2. So we're going to find the vertical component. Fy equals F sine theta. Fy equals 6 newtons sine of 41 degrees. So Fy is equal to 3.94 newtons. Okay? And then let's do orange for Fx. Fx equals F cosine of theta. So now we're going to substitute everything in. So we're going to put in 6 newtons cosine of 41 degrees. Fx equals approximately about 4.53 newtons. So really, really important idea here is that, and I'll write this in red, that this is my net force, okay? F net is equal to F of x, all right? So let's label in our Fx and Fy on our free body diagram. So all that looks like is the following. So this is Fx, Now we'll draw in Fy in blue. That's all it means. That's all it's supposed to look like. All right. And now we have to ensure that our vertical forces cancel out. Clearly, Fg and Fn are the same magnitude, opposite orientation, so they just cancel out. So we don't have to worry about them anymore. So we're just left with this horizontal force, which, like we've said, is now our F net. So I'll write this work in red. Oops. So, our formula is A equals, I'm sorry, I guess my hand's touching my iPad, F net over mass. So then we substitute in everything. So we say F net, that is 4.53 newtons over 10 kilograms. And we should get an answer of 0.453 meters per second squared. Do not forget your units. The units for acceleration are still the same as what we used to do in kinematics. Okay, but other than that, it's pretty simple. All the following examples after this are the same thing. So you follow the same exact rules every single time. And if you follow the rules, the steps, you'll be successful 100% all the time. Okay?